Silvia, thanks, Silvia, for. Is this the right way to pronounce your name? I'm not.
Silvia is the right way to pronounce it. The last name is going to be the hard part.
Okay, what's your how to pronounce your
Sellán.
Yeah.
Yeah.
Is that the French?
It's Spanish.
Oh, Spanish.
It's Spanish. Yeah.
All right. Yeah. Thanks for visiting us here today. Great pleasure to have you here. Silvia is first-year computer science PhD in University of Toronto, working with Alec Jacobson, who some years ago was a postdoc here, and then moved there. Silvia is doing a great job, great work. Even before I know her, I read quite a few number of papers. She apparently doing great. She when the Adobe Research Fellow, right? I think last year. And now she's about to graduating. So apparently with this very short title of the talk, just go ahead.
Thank you. Yeah, thanks everyone for coming, and thank you for having me here. I started my PhD in 2019, so since then I've only given talks on Zoom ever since I started. So it's great to be here in person. New York City is beautiful. So I just want to thank Hongling and Purvan for having me here. And yeah, since I've never done a talk in person, I thought I would start by introducing who I am and the kind of projects I've worked on, and then I'll go into depth into one specific one that I've done lately that I'm most excited by. So anyway, I call this talk geometry because that is the field that ties all of my work together: how to capture shapes, how to store them, how to study them, how to transform them. Some of my work can be seen as addressing types of fundamental geometric problems. I need to look at my screen because I can't see this, but it feels like I'm not looking at you guys. Anyway, yes. So anyway, some of my works tackle fundamental geometric problems. So I thought I would show you some examples. So this project that I did with Norm Eigerman from Adobe Research and my PhD advisor, Alec Jacobson, it tackles the following question. Imagine an object that's moving through space following some trajectory. A very challenging geometric question is, what is the region of space that is covered by this object? This is called the swept volume of a shape. And basically in this work, we propose a completely new way of computing it that's faster and more efficient than previous work. Why would you want to compute something like this? Well, if you manage to compute it robustly for complex geometries and complex trajectories, you can test whether the proposed trajectory intersects with a collider or not, to know if you should take that trajectory or not, or if you should look for a different one. So that's one example of a fundamental geometry problem. There's a geometry in the form of a shape, and a trajectory, and geometry out in the form of another geometric object. Here's another one. This is a joint work with Jacob Kasten, Yanxing and my advisor, Alec Jacobson. You'll get tired of his face. And the idea is we propose a new way of smoothing a shape such that we only smooth the concave regions of the shape, but we keep the convex regions with the same discretization. There's a bit more mathematical fundamentals to it, but basically that's how I would explain it in one sentence. Why would you want to do this? Well, it's a very fascinating mathematical problem, but also you may use it to simulate how rust accumulates on something, because rust accumulates only on concave regions, not on convex ones. And most importantly, you would use it as a way of simplifying shapes, since the output always strictly contains the input, because you're only smoothing the concave shapes. Then you can use it as a cage for things like simulation or animation. So this is another fundamental geometry problem. We have an input that's in the form of a geometric object. We have an output that's in the form of another geometric object. The mathematical problem in the middle is interesting to a geometry person, and we solve it using geometric method. Good. So that's why I called it geometry, because it's all full of geometry. But lately, I've been moving away from these types of fundamental geometry-only problems into something that I like to call Geometry Plus. Now, Geometry Plus is not it's not a subscription service where you pay $10 a month and you get a new triangle in the mail or anything like that. It's actually much more simpler. It's a plus in the traditional sense. It's a plus in the sense of you take geometry and you combine it with something else. So we look at problem, we take a geometric lens and join forces with other fields, and ideally that the sum is greater than the sum of its parts, and we can find new problems and new solutions that we couldn't think about by just looking at it as a geometry problem, just looking at it from the geometry lens or from the other fields lens. So this geometry plus idea has been guiding my work for the past 3 years, and hopefully I can convince you that it's an interesting one, and I'm going to do it by telling you about a few problems. I think the most clear example is this work. This is a work where we bring a new perspective to a very classic, very well-studied geometry processing problem, but we look at it from the lens of signal processing. And this is, again, a joint work with Noam from Adobe and my advisor, Alec. The idea is we got interested in this concept from computer vision and signal processing called compressed sensing. The idea is that you sample a signal, in a way that you capture its most important features so that you can recover it with the least number of samples. There's a lot of more math, but basically how to find the dominant features of a signal. An image or an audio signal is what they usually consider. So we read about this thing called compressed sensing, and we had an idea. What if we treat a surface as a signal? Now, of course, just a surface as a signal is a weird thing to consider because, there's no zero signal that is equivalent to a zero surface. It's a bit strange. But what about if we treat a differential quantity about this surface as a signal? So in particular, we effectively consider the second fundamental form of the surface, which is just a differential quantity that measures the curvature of the surface. And we use the tools of compressed sensing. Effectively, we sample this surface as a person from signal processing would and learn its dominant features. And turns out that this makes the curvature have some properties which make this surface easier to fabricate, or in geometry terms, it makes it developable. I like to start with this example because it's one where you really needed the sum of these two things. You really needed to understand the concept from signal processing, but just by looking at it as a geometric problem, we would not have thought of this idea. And just by looking at it as a signal processing problem, we would not have thought of this idea. It needed the combination of insights from geometry to understand what the second fundamental form was and what that curvature meant and what a developable surface was, and insights from signal processing to understand what compressing this second fundamental form was. So that's one example I really like. Here's another one. This is a work where we combine geometry with numerical analysis. This is a joint work with Heng-Yi Chen, Mitchell Dembowski, and my advisor, Alec. The idea is that when a person that works in numerical analysis, a mathematician, talks about solving a PDE numerically, their input looks like a domain and some equation. And that's basically where they start. And then they design very fancy methods to solve that partial differential equation on that domain. But as geometry researchers, we don't need to start with the domain. Instead, we have geometric insights into how a domain was initially constructed. So in this work, we use those geometric insights, for example, knowing that a domain was constructed via constructive solid geometry, so by combining, by basically doing unions of shapes, to solve a PDE numerically. So this is another example where we needed to combine these two areas. A person that does just numerical analysis would only have started in the middle and solved a very hard to solve PDE equation, but we make it trivial by leveraging insights that we have from geometry. Anyway, that's another example. Another example that I'm particularly proud of is this work. This is a work where we look at existing algorithms in our field from the lens of algorithmic fairness. I did this work together with my co-first author, Anna Dodek from MIT, and Professor Theodore Kim and Amanda Phillips. In this paper, we surveyed computer graphics algorithms, and specifically, we looked at algorithms that generate geometries of the human body, and we studied how they currently treat gender as an algorithmic variable. And if you read the paper, we go into depth into different harms and biases that can be introduced by doing so. Another recent project I've worked on is this one, where we combine geometry with physics simulation, and we use geometric insights to solve a classic physics simulation problem, which is how does something break when it receives an impact? This is a joint work with Jack Long, Leticia Matos da Silva, Aravind Ramakrishnan, Yushan Yang, and my advisor Alec. And the idea is very, very simple. If you worked in simulation, you know, or even in physics, you know about this thing called vibration modes. These are the most natural ways a shape has of vibrating, or if you're a physicist, the lowest energy deformations that form an orthogonal basis. We do a small tweak in how these vibration modes are designed and build an object's geometric fracture modes, or basically what are these most natural ways of breaking or separating, or lowest energy. These modes can be pre-computed for a given shape, like this one. And since they form an orthonormal basis of the space of impacts, they can be used to project any impact in real time and get impact-dependent fractures, meaning that, you know, if the impact is different with the same pre-computation, we can produce different fractures. You can, I always like to imagine the video game The Legend of Zelda, where you have pots and the pots always break in the same way, regardless if you hit them with a sword, if you put a bomb next to it, they always break in like the same 4 pieces. With an algorithm like this, it would break differently depending on what the impact is. And this is a very mathematically also a very interesting work, or at least I found it very interesting to work on it. One of the reasons I find it interesting is because breaking things is very fun. And if you simulate it, you break and you don't have to clean up, right? So it's even more fun. But there's, you know, even if breaking things is satisfying, it's also equally satisfying to see them put together, sort of play it backwards like that. And you know, seeing using breaking things to put them together is what this other work is about. So this is actually a collaboration that I didn't see coming, where we explored applications of our fracture simulation with robotics and machine learning. So this was a collaboration where I teamed up with my 2 co-first authors, Yunxin Chen and Ziyu Wu, from the robotics department from the robotics lab in our department, who are advised by Professor Animesh Garg, and of course with my advisor Alec Jacobson. And the idea was, you know, and this is kind of, I found it very interesting. We made this algorithm that simulates fracture very fast. And as graphics people, we thought simulating something fast means you can do it in real time and use it in a video game. So when you do something in a millisecond, to me as a graphic person, I think, oh great, you can do it every frame. You can do it in a video game. But for a machine learning person, when you tell them that you can simulate something very fast, what they think, or what these people thought was, well, that must mean that you can do many of them in like one day, right? So it was a completely different perspective into what it meant to do something fast. So we used our algorithm to simulate 1 million different fractures. And this took like 1 day because we specifically designed our algorithm to simulate things very quickly. So we made 1 million fractured objects, and we used it to train reassembly algorithms. And specifically, not just to train them, but to benchmark them. So there's all these algorithms that take pieces and try to put them together. We used our data set to benchmark them, and turns out they're pretty bad. So we, you know, this was a collaboration I never saw coming, and I hope that by releasing this data set into the wild, we can show that there's a lot of work to be done in this field and hopefully become a benchmark for future algorithms. So anyway, now I took you on a tour of what this geometry plus means. I'm going to go more into depth into this project. This is the last project I've worked on, one I'm particularly fond of, and I would like to explore many future works directions. And it's a combination or a way of reframing a classic geometric problem from the lens of statistical learning. This is a joint work with my amazing advisor, Alec Jacobson. I didn't add his picture here because I thought just adding one picture would be like too egocentric, but it's still him there. By the way, if you have any question, I forgot to say this, just raise your hand. I'm happy to stop, and especially because I'm going to go a bit more into depth in this one. So if you ever get lost, feel free to put your hand up. So the question is simple. We have a point cloud like this. This is an oriented point cloud. So a bunch of points and a bunch of normal vectors. And my question is, let's put an object somewhere in the plane. Does the object intersect the surface described by the point cloud? So of course, it doesn't touch any of the points, but the points are a discrete representation. We assume that the points come from a complete smooth surface. So does the car hit that surface? That's a hard question to make. I wouldn't know how to answer it just from these points. Maybe what I would have done a year ago, and perhaps what you would do too, is use the surface reconstruction algorithm. So I would take these points and I would turn them into a fully determined surface, and then we would test if that surface intersects the car. And the most well-known surface reconstruction algorithm is Poisson surface reconstruction. You might have heard of it. Basically, Poisson surface reconstruction generates a scalar field that looks like this, that takes negative values inside the shape and positive values outside the shape. And if it takes negative values in, positive values out, that means that the zero level set, so the points that have value 0, are the reconstructed surface. So does the car intersect the point cloud? Well, it doesn't hit this surface, right? So at least Poisson surface reconstruction lets us answer the question, or it gives us an answer to the question, something like this. According to Cashin and al., that's Poisson surface reconstruction, it doesn't intersect the surface. That's a bit of a scary conclusion to reach, right? Because put yourself, imagine you're the one driving the car. Do you want to be that sure? Would you be that sure as Poisson surface reconstruction? Now, statistically speaking, and I hope this is the perspective that we slowly build up in this talk, there are many possible surfaces, right? Point cloud reconstruction is an underdetermined problem. So yes, the surface could look exactly like the Poisson reconstruction one. I'm not saying it couldn't, but it could also look like this, or like this, or like this, or even like this, right? We have no idea what the surface looks like. And yes.
That's a very naive question.
Sure.
I don't know in the space. So why do you not just have a point cloud in the first place? Why do you have this norm? Like, in what situation would you have this data in the first place?
So this is usually the output of a 3D scanner.
Okay.
You have ways of estimating the normals, the normal directions, and that's like usually very useful information that you can get fairly easily. Usually by looking at like things like RGB data, the reflections that tells you like the not just where the point is, but how it's oriented with respect to the scanner. So this sort of point plus direction is the standard way we deal with point clouds in computer graphics, because and this is like kind of hand wavy. If you talk to someone from computer vision, they'll say, well, it's not as trivial to get the normals from the point cloud, but this is this is the input to Poisson surface reconstruction, so that's why I use it as an example.
So ShapeNet, for example, which is a data set where they basically scanned a bunch of shapes.
Yes.
There are point cloud reconstructions that are not normals. That's kind of like the best guess. It's not actually necessarily the correct point cloud, would you say?
I don't understand the question. Can you say that again?
Just because you're trying to reconstruct the surface, right?
Yes.
Right. So,
Yeah.
but then I'm assuming that, so you're going from normals to point clouds, right?
No, this is a point and a normal.
Because then you're trying to go from that to surface.
To surface.
Got it.
That's right.
Okay.
That's right. Right. So the surface would be like the outline that I draw, and the input, what we have is a bunch of points and a bunch of vectors.
Oh, I
So
got
like
it.
that,
Okay.
that is the input.
Got it.
Do you have an assumption on the topology of the surface?
No.
Like, is it water? Oh, okay. Just saying.
It's a solid.
I see. Is it
So-
watertight? Is it close? Or not really?
I mean, it has to be closed for it to have an inside, right? I
I
guess
see.
the assumption that we have is that this scalar field that's negative inside and positive outside has some meaning.
I see.
We could probably do something similar for open surfaces, because that, Poisson reconstruction would sort of like vanishes, but then you'd have a zero. So yes, let's assume that it's close.
So you always have usually boundary conditions on that, because you can have open surfaces if you specify like knowing them.
No, so like the output of the method can be open.
Yeah, that's right.
Yes,
Yeah.
but that's sort of a failure case. Like the assumption that we're making is that it's solid.
And they're okay.
Yes, because otherwise inside has no meaning.
Right.
So
It's still like, because you're gonna define a GPU for this, right? And you
yes,
can still define a GPU for.
yes,
Yeah.
everything I'm saying will have an equivalent if it's an open surface. The problem is that if it's open, it's going to be much more complicated, because it'll only be valid in like the subspace. You're going to have to assume that you're looking at like a zoomed in version of the surface where you're only seeing a part of it, but you still have to decide like that some part is inside and some part is outside.
Was it just for the partition? Half?
Yes,
Yeah.
exactly. Then
Yeah.
we'll,
Okay, maybe-
no, it's fine. We'll look at
Yeah.
we'll look at the problem of outputting open surfaces later, and I think it'll become more clear. But for now, just for like stating the fundamental problem, it's assuming the surface is closed. So anyway, as I was saying, we have the car there. Poisson reconstruction told us that the car doesn't crash into the surface, but we decided that it's a bit of a scary conclusion to reach because there are many possible surfaces because it's an underdetermined problem. And some of these surfaces will intersect the shape. Some of these surfaces will not intersect the car, right? So in a way, Poisson surface reconstruction by Cashton et al. Is projecting to one possible surface and answering, and it would give us an answer for that specific surface. So the work that we present today will formalize this statistical intuition that I was building up to, that there are many possible surfaces, and give us a more complete answer to these kinds of questions. And it turns out that these answers won't just be useful for collision detection, they'll also be useful in other applications like raycasting, next view planning, or point cloud repair. Okay, so how? We'll achieve this by combining the Poisson reconstruction algorithm with insights from statistical learning theory. So specifically, we'll combine it with the concept of a Gaussian process. So this will require that we understand Poisson surface reconstruction in a specific way, and it'll require that we understand what a Gaussian process is, and we make some specific assumptions on Gaussian processes. So let's do each of these separately, and then I'll show you how to put them together. Poisson reconstruction. Poisson reconstruction has been around for like 15 years now. And if you've worked in this field, you might have an understanding of how it works. I've been talking about Poisson reconstruction for the past year. And it seems like every geometry researcher or many geometry researchers have a good idea of how Poisson reconstruction works. But something I've noticed is that each one has a different idea from the previous one. And they're all right. They're all correct. The problem is that Poisson reconstruction is such a fundamental work that it's kind of these things where you see whatever you want to see in it. And some professors see it as, oh, it's approximating an integral. Some professors see it as it's solving a partial differential equation. Others see it as, oh, it's just an interpolation problem. There are many ways of understanding Poisson reconstruction. So if you have an understanding, I ask that you set it aside for 5 minutes, because I'm going to tell you how I think of Poisson reconstruction. We're going to need to look at it that way. I promise you that what I'm saying is correct. And if you look at it the same way I do, it'll become much easier later. So the input to Poisson reconstruction is an oriented point cloud, which mathematically is just a bunch of points and a bunch of vectors, or a bunch of tuples point vector. The first thing Poisson reconstruction does is an interpolation step. So it goes from that discrete set of points to points on vectors to a vector field that's defined in every point in space. This is a bit of math, but basically all that this is doing is a weighted combination of all the vectors in the point cloud. So it makes sense. It's just the way we do in interpolation. The weights in this combination are proportional to this kernel function. No need to understand what this does. Basically, it's bigger the closer 2 points are. So it makes sense that since you're doing an interpolation, the closer 2 points are, the closer, the more influence they will have on one another. That's just a normal interpolation. And there's this bit that measures local sampling density. It becomes obvious why we need it if you think about it for a bit, but let's not get into it. Basically, we end up writing this as a matrix, like as a matrix multiplication like this, where K and D come from the sampling density and this kernel function. Basically, just a vector and a matrix inverse. That's diagonal matrix inverse. So once we've defined this vector field, that's a vector for every point in space, we solve a partial differential equation, and that gives us the scalar field. This partial differential equation is a Poisson equation. That's why we call it Poisson reconstruction. But actually, this solve PDE step is the one I'm not interested in. So let's not think about it yet. All that we care about from here is this equation. So this is just an interpolation problem where we go from a discrete set of vectors to a vector defined for each point in space, and we do it using that equation. this is what the Poisson reconstruction people do. Our main contribution, the punchline of what I'm saying today, will be that I'll show you what a Gaussian process is, this concept from statistical machine learning, and I'll do some assumptions and I'll reach exactly that equation. So this is the only thing that you have to take away from this slide. Then we'll get to exactly that same equation, and that's going to give us the big insight. So let's talk about what a Gaussian process is. A Gaussian process, in a way that's trendy today, is a way of doing supervised learning. It sounds fancy. But as someone who doesn't do machine learning, I need to actually explain what that means. It just means that there's some function that I want to know, and I don't know what that function is, what that function looks like. I haven't seen any data for this function either yet. If you like if you're the kind of person that likes to think with an example like me, I like to think of it as how long does my advisor take to respond to an email? So X is the time of the day between like 0 and 24, let's say, and U is the number of hours, days, depends on the advisor. So the first thing we do is we set a prior. This prior in Gaussian processes comes in the way of two functions, the mean and the covariance function. No need to understand exactly what these do. This is basically just encoding the knowledge that you may have about this before you see any data. So you might think, oh, if I send my advisor an email at 2 a.m., it might take longer than if I send it at 1 p.m. And I might hope for like a 2-3 day response period, something like that. Your hopes before you see any data. The next step is you observe some data. So you send him or her a bunch of emails. In my case, it's him. I send him a bunch of emails at 10 a.m., 1 p.m., 2 p.m., 5 p.m., and I log how long it takes for him to answer. So we do that. We basically observe some data of this function. And the cool thing about Gaussian processes is that then we get a posterior distribution. So it tells us how the probability of the value of the function at a new point is distributed. So for example, say I sent him an email at 1 p.m., it took however long, and an email at 3 p.m., it took however long. I can ask for a new point that I haven't seen. So at 2 p.m., if I sent him an email at 2 p.m., what is the mean and the variance of the time that it would take him to answer? And the cool thing about Gaussian processes is that these two, this mean and this variance, answer to some closed form matrix multiplications. So we don't need to sample a function. We don't need to do any like variational stuff. It's just a bunch of matrix multiplication. So that's basically the big power of Gaussian processes, that just by observing the data, we can state the posterior distribution. And there are a lot of Gaussian processes, but they all go like this. You get a prior, you observe some data, and then you get a posterior distribution that's normal with some mean and some variance that you can compute. This is just what a Gaussian process is. Now, there are a lot of simplifications that we can do on this process. One very common simplification that people do in Gaussian processes is to assume that the mean is 0. This is simple because for any Gaussian processes with non-zero mean, you can always consider the Gaussian process of that Gaussian process plus the mean, and then you would get a 0 mean Gaussian process. So this is actually something you can do without loss of generality. And it actually is very helpful because it turns this equation into this. So it makes it much simpler. Now, if you've done numerical analysis, you're looking at those equations for the mean and the variance, you might be thinking, wow, what does that -1 mean? Like, I'm inverting a matrix. What does that matrix look like? Like, is that going to be robust? Is that going to be efficient? How long is that going to take? So let's look into it. This K is a matrix that looks like this. It's not actually tri-diagonal. It's all I mean by this representation is that in each row, this matrix is mostly going to be sparse. So almost every entry is going to be 0. And they're all positive. The center value, the diagonal entry, is going to be the biggest value by far. And then there's going to be a bunch of off-diagonal entries that are much smaller and positive, and they measure how close two training points are to one another. Okay, so if you've done simulation in the past or physics at all, you might be thinking that this is kind of like a finite element mass matrix or a boundary element mass matrix, because it's a sparse thing that measures how close 2 points are, and it has a very high diagonal values. They're all positive. So this is what I thought, at least, as someone who has worked in finite element analysis. And the cool thing is that in finite element analysis, we don't usually work with this mass matrix. Instead, what we do is we lump it. We basically ignore every non-diagonal entry and just take the diagonal. So I thought, since that's legit in finite elements, let's do it here too. So I call this matrix D, and I changed it over there. And then we're inverting a diagonal matrix. So that step that looks so scary now is trivial. Now I realize that what I've just said is a bit hand wavy, and actually, mass matrix lumping in finite elements is a very, justified process that's done with like a variational justification. In this case, there's very, sure. Yes. Yes. So what do I lose? This is a good question. So if I rephrase your question, how legit is it? Like, how can you actually just make it diagonal? So we show that you don't lose much. So under some assumptions, we show in like a paper appendix, you can show that it's justified, with some assumptions of how close the points are, how far they are, how many of them there are, compared to the sample point. It's somewhat legit. There are some other cases where it's not. And in fact, 2 weeks ago, there was this paper that came out. It's on archive right now. That basically shows a way of doing this lumping, but well, without the hand waviness and in a more smart way. So
which kernel function are you also using? Because it probably depends heavily on your choice of getting right. Is it like the data? Yes, I was trying not to get into that much detail, but like basically to answer the specific, we're using compactly supported normal kernel. Okay, so it's the same like BCA one from the Poisson paper? Like,
yes,
yeah,
okay. Yeah, it's exactly that one. Yeah, because we want to reach that one, so that's the one we're using. But basically, like that's just like, yeah, that's the answer. This result is actually agnostic of the kernel that you use, as long as it has some assumption. So this is a paper that basically teaches you what matrix to put there instead of D, that it still keeps the inversion easy, but doesn't lose a lot of information. And if I wrote the paper right now, I would just do this, but this wasn't out when we did it, so I had to do this this covariance lumping. So anyway, this is to say that we reach mean zero Gaussian process with a lumped matrix. The last thing we're going to do is, I told you, the example I gave you is how long my advisor takes to respond to an email. That's a scalar function that's measured in hours or weeks sometimes. But we can just as well use a vector valued function. So the same way we did it for U, we can do it for V. And basically, this just means it's a Gaussian process in every coordinate. Okay, so this is where I wanted to get to. It's a zero mean prior Gaussian process with a lumped variance matrix and a vector value. Now look at that equation. That equation, the mean of this Gaussian process, is the vector field from Poisson reconstruction, as advertised. And this was our key insight, or the aha moment that we had. We noticed that if we define a Gaussian process with some assumptions, we get the same mean as the vector field from Poisson reconstruction, but we get much more, right? If we now understand Poisson reconstruction as wanting to do this Gaussian process from the start, we will not only have a mean, we'll have a whole distribution. So this is what we realized, and that realization lets us introduce our generalization of Poisson reconstruction, which we call stochastic Poisson surface reconstruction. That's just branding. What this means is that the input, which was which was a point cloud, as in the output of a 3D scanner, something like that, a bunch of points and vectors. Now it's not just that. Now we can understand it as samples from a statistical distribution. The interpolation step that earlier was just we have a bunch of vectors, we want a vector field defined everywhere. It's not just an interpolation, it's a Gaussian process with some specific prior that gives us a whole vector field posterior. So now we don't just have a vector field, we have a distribution of vector fields, meaning that for any point, we don't just have one vector assigned, we have a bunch of possible vectors with different probabilities. Okay, now that we have this vector field posterior, the same way that we solved a PDE before, we solve it in the space of distributions. And we get a scalar field posterior distribution with a mean and a variance. The mean looks a lot like the Poisson reconstruction output, but the variance is completely new.
So
Yes.
how do you do that step, the PDE step in practice? Do you have a sample or?
The PDE step in practice is actually very easy, and I'll talk about this more later, but it's just since it's a linear operator, it carries over the Gaussianness. So you're basically just solving a linear system with a bit more care, and that it's the same as the system that you solved before, but now you also solve it for the variance. Right. So what does this scalar field posterior mean? It means that for every point in space, we have a mean of what the scalar function looks like, but we also have a variance of what the scalar function looks like. And this gives us a whole Gaussian distribution of what the scalar value at this point is. This Gaussian distribution is fully determined by the mean and the variance. And if we change the point, we get a new mean and a new variance, which gives us a new Gaussian. Points that are very near the point in the point cloud, so very close to the data, will have very small variances. So we'll be more certain of what the scalar value looks like at that point. While points that are far from the data will have higher variances, leading to wider Gaussian distributions. So I thought this was very mathematically interesting. Now I understand statistically what information Poisson reconstruction is actually gathering. But it's not just interesting mathematically. There are many quantities that we can compute using this distribution. For example, this integral. This integral is just the probability that the scalar field is smaller than 0. But in Poisson reconstruction, being smaller than 0 meant being inside, right? So this is just the probability of a point being inside the reconstructed shape. We can plot this for every point, and we get something like this. And now this is a function between 0 and 1 that actually has statistical meaning. It means how likely is each point to be in the reconstructed surface. We're no longer projecting to one single surface. We have a statistical formalism. And we can do it for 3D examples like this one. I'm going to keep using 2D because it's simpler and we can look at the whole scalar field. But imagine that everything we do, we can do it in 3D too. This probability is useful. Intuitively, one thing it's useful for is to quantify how good a reconstruction is. So if I show you these two pictures, there's obviously one where we are much more certain of what the reconstruction is, and there's one where we are much more uncertain what the reconstruction is. So the one on the left, I still have no idea what that surface looks like. The one on the right, I have a pretty good idea of what that is. But by using these probabilities that we introduce, we can also define a thing called integrated uncertainty, which just measures how far from 0.5 these probabilities are. And this is a quantity that goes to 0 if we sample more and more points, which makes sense. So this gives us a way of measuring how good our reconstruction is. And the cool thing is that this is independent of what the surface that we're reconstructing is. This is just a universal quantity. So we can use it when we start scanning something as a threshold. So we can say, let's scan until the integrated uncertainty is some value. And if we do this with different, random camera parameters and random positions and random shapes, we get consistent quality reconstructions because this integrated uncertainty is a measure of reconstruction quality that is agnostic. So this was useful. Another query that we can answer is, where does a ray intersect the surface? Now, there are many possible surfaces. So if we cast a ray against the surface, once again, we're not going to get just one collision point. We're going to get a whole distribution of possible collisions. And this, just by looking at the point cloud, is very hard or impossible to compute because we don't know what this distribution of possible surfaces is. But Thankfully, we can do it thanks to these probabilities. So we can interpret this field that measures the probability of a point being inside the reconstructed shape as differential probability of a ray terminating. This is not that weird because when people do volume rendering, what they say is, my ray is going through a volume, so I'm going to somehow model this density of this volume as the probability that the ray is crashing into a particle. So in a way, we output directly the probability that volume rendering people need. So basically, we can interpret this as the probability of the ray terminating and use it as a volume rendering problem. Then if you've ever done volume rendering, this will be obvious. If not, trust me that this makes sense. We can compute this thing called the transmittance that just measures how likely is a ray to travel this far without hitting anything. And we can sample from it to get the same distribution. So using our probability field, we can get these distributions. Not just for that 2D toy example. So for example, we simulated a scan of this spaceship. I don't know if you can see it, but the left side has many points. The right-hand side has few points. So we place two cameras, one looking at the left side, one looking at the right side. We compute this probability field in 3D, and we see that the collisions from the ray that's looking at the certain part are much more certain, whereas there's a wider spread for the collisions of the camera that's looking at the uncertain area. So this checks out. We can actually combine these two concepts, this ray casting idea with the integrated uncertainty that we introduced before, for problems like next view planning. So for example, if we have the scan of an object, we can place a bunch of candidate cameras and we can simulate casting rays from these cameras, we can first compute the integrated uncertainty of the object. So how good is the reconstruction quality? We can simulate a ray from the cameras, add those new points to the point cloud, the intersection points, and ask how better did my reconstruction get? So how much did the uncertainty change? And this lets us score cameras by how good or how bad they would be as next reconstruction next scanning position. So these are all things that we can do just by computing this integral. So hopefully I can convince you that this Gaussian thing isn't just mathematically interesting, it's interesting for many applications. There are other statistical quantities we can compute. For example, this probability, this value measures how likely a point is to be on the surface. Looks something like this. It's similar to the thing we had before, but this measures the probability of being on the surface, not in the shape. This is different. I think this could be useful for machine learning applications where you want to sample near the surface of an object that you, in training, you still don't know what the surface is. So you could, quantify that uncertainty and sample in these regions. I just came up with that application a few weeks ago. So it's not in this talk. Actually, the application that I have here is maybe less smart. It's point cloud repair. So one thing we thought you could do with these quantities is if we have a scanning of something that's incomplete, we can compute these probabilities of being on the surface and use that as a map to sample from. So if we sample from this probability, we basically fill out the missing parts of the point cloud with new candidate points. So that's what we use this query for. And you might be thinking, what about the car that we started with? Does the car hit the surface or not? Well, another quantity that we can compute using this statistical formalism are regional probabilities. So I show you that we can compute this thing that measures for an individual point, what is its probability of being in the shape? That's for one dimension 0 point. But we can actually draw whole regions and ask what their probability of intersecting the shape is. So like the probability that a region that I draw has non-zero intersection with the shape. And this is exactly what we needed for the car example. So I made this very simple realistic scene in Blender and placed a hypothetical car, scanned it, simulated a noisy scan of its surroundings, and the car can compute its likelihood of colliding all along the path. Yeah, this is different than what Poisson reconstruction would have done, which would have just told us yes or no. This actually quantifies the probability of colliding. So anyway, these are some applications that we managed to do. and introduced with this new methods. But actually, you know how actors would do one for you, one for me. So like they'll do one movie that sells a lot, so they can do the other movie that they really, they like doing, and they know they're not going to sell as much with that one. These are the applications I did for the reviewers. These are not mine. This is the one I like. So here's the one that's for me. So the cool thing about this project is that we looked at Poisson reconstruction as a Gaussian process. Specifically, we had to assume that it was a Gaussian process with a given prior and mean zero. We had to do this so that we reach the same formula, right? So, but now that we understand it like this, we can be, more presumptuous and think, well, now that we know that Poisson reconstruction is in some stone tablet passed down through generations, now that we understand what Poisson reconstruction comes from as this Gaussian process, can we do better than Poisson reconstruction? So specifically, does this zero mean prior make sense? And I think not. I think you can do better. I think you can think about the specific tasks that you're doing and use different priors depending on the task. So one problem or feature, I don't know, Francis might disagree with me, is that Poisson reconstruction sometimes outputs open surfaces, or like, let's call it a problem. They sometimes outputs open surfaces, despite me knowing that it can't be open, right? So if I'm scanning a car has to be a closed surface. It's not an infinite car. But Poisson reconstruction, just the way it's formulated, has no way of, imposing this prior knowledge that it's a closed surface. But by doing a small tweak in our prior, now that we understand it this way, we can just force it to be closed. And this is a problem that there have been entire papers written about how to make Poisson reconstruction closed. But now that we understand it statistically, it's just adding a small, it's one line of code to the prior. And that doesn't just work for simple 2D examples, it also works for simple 3D examples. So if we do a scanning of this very simple apple and we use Poisson reconstruction, it looks like this. It looks open. And this is, once you see it, once you see that this looks like the Plants vs. Zombies bad guy, you can't stop, you can't unsee it. So yeah, my husband said that, and since then, all I can see. So it's open, which isn't, there are very few open apples in the world. So we can add that prior knowledge, and ours outputs a closed apple, which is already pretty good. And as you can see, we can also output the variance, so we know the regions that we're less sure about. An apple is admittedly a very simple example, but we can do it for more complex geometry. So this car, we can simulate a scan of it. This is what Poisson reconstruction looks like. Again, not that many open cars, but with a very simple tweak in the prior, we can get something like this. And this is like a very simple geometric prior. I'm not doing any machine learning here. Sort of, this is the exciting, this is why I said this is the one I did for me, because this feels like the beginning of something. So if these very simple priors are just adding one line of code to the reconstruction, can already be so good and so much better than Poisson reconstruction, what else can we do if we actually dedicate time to think about it and we actually learn from data? So I think a very promising avenue for future work is, how do we incorporate task-specific priors to the reconstruction? So if I'm going to be reconstructing cars, how can I learn from a million cars what a car looks like? And then when I reconstruct a car, I can just project that prior knowledge. And that, forget about our variance and all of that, those fancy quantities. This will improve the reconstruction itself, right? This is new understanding that will let us formulate a new Poisson reconstruction, even if we don't care about that uncertainty. So anyway, that's one avenue that I think is fun for future work. Another one is improving the runtime of the algorithm. So computing our mean is very fast, but computing this variance is very, very slow, dramatically slow. The reason is because of this solve PDE step, which I briefly hinted at earlier in response to the question. But basically, this solve PDE step, I didn't talk about it because it's not interesting. We just set a grid, and solve it as a bunch of linear systems. Getting the mean is just solving one linear system of size m cube. M is the grid size. So that can be done pretty fast. But getting the variance, since it's a matrix equation, and it means solving m cube linear systems of size m cube, which is m6, right? And m6 in computer graphics means infinity. So this is very, very slow. M is the number of grid cells along one dimension. So 100. Right, so that. So this is very slow. So we don't actually do this in our work. In all the examples I showed you, what we do is we do the classic computer graphics trick of projecting to a subspace. So we actually take the eigenvectors of the Laplacian on this square, and we solve the equation, project it to that subspace, and that makes it from very slow to slow. And this is a bit disappointing, right? Because this is not a very complicated function. This is not a fractal that I'm showing you, or some weird, topological function. This is a very simple, it kind of looks like delta functions, right? It's not delta functions because it's passed through this Laplacian solve, but it looks very simple. So I think that a very if it's what, November something. If you want to write a SIGGRAPH paper and you don't know which one, you still have time to just write, learn what this function is like. And it seems like a slam dunk because we'll provide all the statistics. All you need to do is do that, and you'll have a figure that says, our paper takes 1 hour, yours takes 1 second, and that's a slam dunk. So that's one thing that I also think is interesting as immediate future work. Another one is a question I get every time I give this talk, so I figured I would add it to preempt it, which is, couldn't you do this with a neural network? That's the question I always get. And I get defensive because I don't know enough about neural networks. So when I get it as a question, it feels like, oh my God, they caught me. I don't know about this. But if I add it in the talk, it's an open question that I'm telling you about. See how I rephrased it completely? So anyway, I've been looking into this called Bayesian deep learning. There are these things called Bayesian neural networks that at least seem to output something similar to our variance. So yeah, I think that if we use these networks for the same task, maybe we could get something similar, but leveraging all the learning from data part of neural networks. More broadly, in this paper, we combined a concept from geometry with Gaussian processes. And something I've also been thinking about for the past few months is what other parts of the geometry pipeline can we use Gaussian processes for? So, I guess part of my intention today is that next time you are working on something or think about your current project or your previous project, is there any part of that project that can be thought of as an interpolation? So these are some examples. But is there any point in my project where I have a limited set of data and I'm interpolating to some new point in that data? If that's true, then maybe you can add a Gaussian process there. Instead of just reconstructing one function, reconstruct a whole distribution, and then you can quantify the uncertainty of your workflow. More broadly, Gaussian processes or not, I hope that this work is in this work, we combine geometry with uncertainty quantification, which is a big field in machine learning. And the vision that I have for the next few years is a fully uncertain geometry processing pipeline. So there are many works that quantify uncertainty in geometry. These are some of them. But the sort of slightly frustrating part is that all of these and ours are focused on the capture step. So, and this makes sense because the real world capture is where you usually have the most uncertainty. You have the most measurable error, you have incomplete data. So it makes sense that the first thing that we want to stochastically understand is a capture process. But then we don't do much with that stochastic captured object. And I think that's a missed opportunity. I think something we should do then is to carry that over through the whole geometry processing pipeline and do things like stochastic numerical analysis, stochastic discrete differential geometry. All of these things we haven't done. We have stopped at the stochastic captured object. I think these will not just allow us to quantify the uncertainty of steps through the along the geometry processing pipeline, but they'll also give us feedback for the captures. So, if I'm interested in some curvature of an object, I can scan it, quantify the uncertainty of my curvature measure, and then bring that information back to the scanner and know if I should scan more or less. So this is, if we manage to take it further down the pipeline, this can hopefully be not just one pipeline, but a circle. And I hope that this work is just one small step in this, admittedly a bit science fiction vision that I have. But to end, the reason that or one of the main reasons I'm here is that I hope I can work on this with you. So I'm looking for people that are looking for projects. I have a bunch that I don't have enough time to do all of them. And the SIGGRAPH deadline is approaching. You all slept from CVPR already, so you're looking for something new to do. I want to end by pitching a bunch of projects in this direction. And if you like them, this isn't like a rhetorical trick. I actually want you to work on them. So send me an email if any of these sound interesting. Okay. So I already told you about a bunch of them. Approximate this faster. Good. Let's learn this with a neural network. Write a SIGGRAPH conference paper. Get it done by January. Done. Another, learn task-specific priors. The question here is just from a bunch of data, learn a vector field. That's the question. Everything else, you can use our code. I'll help you. The task here is only learn a vector field from existing data from a task-specific data set. Again, this is like a 1 month long thing that we could do together. If you're up for it, January 25th. Another one. This one needs more work on your hand. Let's use more Gaussian processes. Let's take whatever you're doing now and add a Gaussian process. Let's take your CVPR paper, add a Gaussian process, and then we get a SIGGRAPH paper too. So these are 3 quick ones. Let me tell you about 3 other slightly more involved ones, but I think the payoff in these are also slightly bigger. So one, we have all these probabilistic surface representations, like the one we came up with. I think an interesting direction is to combine them with specific 3D scanning techniques from computer vision. So geometry plus computer vision, if you wanted to make some branding stick. What do I mean with this? I mean that there are all these computer vision algorithms that take a real world object as input, because if you're a computer vision person, I know some of you are, the real world is the input, which I think is a great slogan. And then they use uncertainty aware 3D scanning. So they already know how to deal with uncertainty. And then they get some depth scan with some quantified uncertainty. And they stop there. For them, a depth scan is usually the output. That's it. For a computer graphics researcher, the input is a point cloud or something like that, some geometry. And we quantify the uncertainty of going from a point cloud to a surface. This is kind of obvious, but I think a great avenue for future work is this arrow. Like, just if you're a computer vision person, pair up with a computer graphics one, could be me. And I'll do this bit of the arrow, you do that bit, and we can write a paper together. If you're a computer graphics person, I'm not jealous, find a computer vision one and do it too. And maybe, let me know about it. But I think this is a fun project to have, because we have these 2 communities that usually live next to each other, but we're not talking. And we're doing the same thing. Yeah.
Oh, sorry, like related to this, is there a way in your paper to incorporate noise from
Yes.
points?
Yes, the thing is, ours is Gaussian isotropic noise, which is not the noise that you get from a 3D scanner in the real world. In the 3D scanner, there's like 2 fundamental directions, which is like, one is the one I'm looking from. Another one is like the orthogonal plane. The noise in those 2 directions is different. So you need to somehow incorporate that. So like vision people perfectly understand this. And every time I give this talk to vision people, they're like, oh yeah, but like Gaussian noise, like a point isn't just a point in space. It comes from like some laser that hit that point. Like it's different. I'm very precise in like the depth of the laser. I'm less precise on like the other dimensions of the laser. So, and I think that we could do that. It's just a matter of talking to a vision person and asking them, what is that noise that you get? And then doing all of this, but with that noise. I think we could do it. As long as it's Gaussian or a sum of Gaussians, we could do it. It's just a matter of having that conversation, I guess. And
Can I ask how slow right now it is? Like you said, it's slow, right?
slow.
How slow, like how many, can you give me a number? Let's see for the funny.
For the examples I show, it's like 2-3 minutes.
Of the
Of-
entire process?
Yeah. The expensive part is the variance.
It's because you are using the subspace, the projector solve.
Yes.
And how many sort of modes are you using?
I'm using 3,000 modes.
Is it-
Yes,
how come
3,000.
3,000?
Yeah.
And that's gonna be ended up with 3,000 by 3,000 system? Or
Yes, but you're solving,
for how many times?
you're solving it 3,000 times.
Okay,
So
3,000 cube,
yes,
okay.
and that's 3,000. You can sort of tweak it depending on like how much error you're willing.
I think this is more from another kind of industry perspective. We are actually having a bunch of scanning tasks.
Okay,
And in industry, the biggest problem is the efficiency.
okay,
Because the data is just huge, it's too much.
okay.
Like every minute we produce like 500 gigabyte data.
Interesting.
And so people care about the efficiency very little.
To be clear though, that the bottleneck in the examples I show does not scale with the number of points. So like our solve bottleneck, you've already like sampled the vector field, you're done.
But for the solving the PD solve, you have to have higher enough resolution.
Yeah.
Right, in order to
Yeah.
resolve the details of the
Yeah.
geometry. And the higher the resolution is, the slower the
Yes.
process.
We're not being smart in this paper. Like we're using a uniform grid, which you wouldn't use. And we have some like preliminary results on an octree that's much more efficient. We're not being smart at all or efficient here. I think that like the project I pitched before about like approximating this variance, I think that would just destroy that concern entirely.
Code we use that?
I will.
Or can I ask you? for
Yes, you
sharing?
can definitely ask me. Yes. Yeah, I'll email me or I'll email you. I'm planning on releasing it like in the next few weeks. I need
Oh,
to,
okay, cool.
yeah.
Because if you're interested, I think there might be some chance to, use this and this in some of the real applications.
That'd be great.
And of course, the one sort of actual precondition is to make it fast enough.
Uh-huh.
And also the prior, like see where, for example.
Yeah.
In the lab, in my industry lab, we're capturing some specific things. like
Yes.
Whatever general shapes. So there might be some, simple, not for papers, I'm not interested in that kind of small thing for writing a paper. But I think it could be useful for like some real application.
Okay. That's good. I do care about the paper, but we can maybe I'll do that part and you guys do the real world part.
Sure thing. I'll I talk to my team.
Okay, that'd be great.
One comment is to handle, different noise distributions.
Yes.
You need to change the covariance function, right? So
That's
this-
right.
Yeah, and I think this becomes tricky with your, with the precisely this thing that you want to speed up, right? I think. You can like, you have a very easy covariance function.
Yes.
In some sense, right? But I think, so like, I have work on like learned kernels, where now like,
Yeah.
you take this K function and you learn it from data.
Yeah.
And you get these excellent like task specific priors.
Uh-huh.
But then if you want to kind of turn them into a GP, like you can't just simply diagonalize. And I don't know if you have any ideas on like what if you have something that say like not shift invariant but rotation
Yeah.
invariant?
I mean, that
It's
would,
like rotation invariant in like high dimensional space instead of like.
That was-
you learn the feature, yeah,
I don't, right now, I don't see a reason why that wouldn't work.
like Uh,
I mean, it works in theory, like in the
Yeah.
program, right? But like, how do you make it work efficiently?
well, it's still the same problem, right? Like, I guess. I understand the problem you're saying, like, how do you learn this variance function efficiently, but in a way that like can serve from different kernels that depend on the noise that you have?
Or if your kernel is like not like sparse, like you can
Yeah.
trivially diagonalize. it.
Right,
Yeah,
right. No, the kernel
there-
needs to be sparse. That's
right,
a
yeah,
constraint.
Yeah.
Yeah, let's, because we're getting in the weeds of Gaussian process.
Okay, after
Let's-
this, let's talk. I wanna
Let's talk, yeah.
go into-
Anyway, this is one project. I'll quickly go through two others. So here's another fun idea. So there are all these probabilistic surface representations. Ours is one of them. How about we do numerical analysis on them? So how do you solve a partial differential equation on a domain that's uncertain? So I wouldn't know how to do this except that recently this paper came out, Monte Carlo geometry processing. Basically how this works is to get the solution of a partial differential equation somewhere, you take random walks from that point until you hit a boundary. And then you basically add a little bit of that boundary condition. And that gives you the solution. This is called walk on spheres. And I thought, well, we have sort of like a boundary. We have this boundary probability. So what if we do random walks and stop them according to some probability? Then we'll solve a partial differential equation on our shape. So anyway, this is like another fairly immediate thing. If one of you is interested, we can talk about it more. Here's another sticker paper. Here's a final one. So I show you this example where we score different cameras based on how good they would be as the next scanning position. Here's exactly how we did it. We computed the integrated uncertainty of a point cloud. How good is the reconstruction? We computed collision probabilities along array. So where does array intersect the surface? We sampled the new from that collision probability to get new candidate surface points. And for each point, or for each camera position, we asked, what is the change in integrated uncertainty? So how better did the reconstruction get? And we score the cameras based on the improvement in certainty. And we did it in this direction, from top to bottom. A very immediate thing that we could do together, if you're interested, is to do it the other way. So basically differentiate with respect to the camera positions. And that way we won't just be able to answer the question, how good is this camera? We can answer the question, what is the best camera? And I think that will be an immediate use case in computer vision in 3D scanning. Anyway, these are genuinely projects I don't have time to do. So reach out to me if you're interested and maybe we can do it together. You'll be the first author. That's my bargain. And hopefully I've convinced you of this geometry plus vision. This is my website. You can find my email there if any of these projects sound interesting to you. I thought I would just end by thanking all of my collaborators for the past 3 years. It's been a very, very wild ride. Thank you all. Huh? Yes.
All right, so I think we'll like skip questions because we have one-on-ones anyway, so
Yeah.
that people can chat with you then. But
Definitely.
thank you so much for visiting and we really enjoyed it.
Thank you. Thank you and Hongling for having me.
Yes. All right, so I'm gonna stop the meeting.